So does anybody have questions about the pressure volume curve?
I have a question about rounding, because sometimes we will get really long numbers, so I don't know if it's how much numbers we need to keep or to keep all of them.
Don't keep all of them. How many to keep? I mean, it depends on, it depends on how many you have to start with.
Mm-hmm.
So if you're working with, dividing a number with two significant digits by a number with two significant digits, don't write out 12 significant digits. I mean, just keep it to the same sort of, about the same sort of significance. Don't. I would prefer if you don't have so many significant digits. Just keep it reasonable. Anything else? So it'll be due a week from today, and next Tuesday no class because fall break. Y'all go somewhere fun?
Going to Chattanooga.
I've been there.
Rock climbing.
Oh, rock climbing. That'll be fun.
Yeah.
It's not going to be icy.
Nope.
That's good.
Colorado just got snow.
Yeah, I heard.
Yeah. I was up there last weekend.
Western Nebraska got snow. It's a few days after I was out there last week.
So there's like a small group.
I'm glad summer's coming to an end, but I don't know about you. I'm not ready for it.
Which is like a lot of places. If you go separately, it's like way more expensive, It's like the aquarium, the skydiving.
I prefer, if you do it in Excel or
It is a boat trip.
Sigma Cloud or something, I would prefer if you
Go in the
printed
river,
it
look at the lake and go back.
a hard copy. Yeah, although I can
Skydive.
take electronic copy, but I prefer if you give me a
When I
piece
was
of paper.
before the sunset.
Okay, so today I want to talk about root systems, and then get into xylem and phloem, and water transport in xylem and phloem. So a bit of review, actually, maybe more than a bit, but we'll start where we start. Okay, so roots. Let's talk about roots. Here's a diagram of the end of a root tip. So here's the root cap. Going back from the end of the root, the phloem is the first tissue that differentiates inside the root in the middle. So here's the immature phloem, the mature phloem is here. Notice that the xylem, the mature xylem is way back here. So the phloem differentiates closer to the tip, or earlier than the xylem does. And one consequence of that is that the plant's able to transport carbohydrates and nutrients, whatever, to these actively dividing and expanding cells here at the tip of the root that are, they're dividing and then they're expanding, and that expansion forces the root tip out through the soil. Okay, so the mature xylem here in the middle, and then a little further back in this elongation zone, we get the immature phloem and then the mature phloem. About the same time that the phloem, or that the xylem becomes mature, we see the appearance of the endodermis with Casparian strips. That's coincident with the maturation in the xylem. I'll get to that in a minute. Casparian strips are important because they block apoplastic transport of water. Around this same area, you see the development of root hairs. Okay, so highly stylized diagram, but you get the idea of what's going on near the tip of the root. Now, this is really near the tip. So 580 microns, that's 0.5 millimeter from the tip of the root. All this is going on really close to the tip of the root. All right, the endodermis, that's this layer of cells that surrounds the vascular tissue in the roots, right here. So exodermis, endodermis. The endodermis develops, as I said, coincident with the maturation of the xylem. And it's characterized by the presence of Casparian strips. What are these Casparian strips? These are, this is a, it's made of a highly hydrophobic substance called suberin. And it's deposited around the cells in the endodermis. And what it does is it blocks apoplastic transport of water. Water can't get through those cell walls in the endodermis. What that does is it forces water coming from outside the root into the xylem of the root. It forces that water to pass through a living cell at some point or another. When the water goes through the living cell, presumably the plant then has some control over the solutes that it allows through or the solutes that it tries to exclude from the vascular system and the root xylem. Okay, so Casparian strip is important because it's found, it's ubiquitous. This feature is found in all plants that have a vascular system. All vascular plants have Casparian strip. Every single one. So presumably it's a useful feature, right? So here's some other views. This one, it's stained red. You can see the endodermal cells, which is Casparian strip around it. Here are some other stylized pictures of the root endodermis. The important point, though, is it blocks apoplastic transport of water. Any water moving from outside the root into the root vascular system, into the xylem in the root, has to pass through a living cell. I mean, it doesn't have to do it right at the endodermis. It can go into a living cell. Here, this blue one shows water entering the living cell. Here's root hair and going symplastically into the xylem. But even if it goes apoplastically at the endodermis, the water is forced across a membrane into a cell, and then a membrane back out of the cell into the xylem. All vascular plants have Casparian strip. So this formation of the endodermis and the Casparian band, Casparian strip, happens about the same place that root hairs start to form on the outside of the plant. And you know, root hairs, this fuzzy stuff, what they do is really increase the surface area of the root. And it aids in uptake of nutrients and substances that are immobile in the soil, that don't dissolve readily in water, in the soil solution. So by having this increased surface area, there's a lot more of the soil that's explored for these things like phosphate, that's not readily soluble in the soil solution. For something like nitrate, it doesn't matter so much because that dissolves in the water in the soil, and as the water moves from the soil up to the root, the nitrate moves right along with it. But for an immobile, relatively immobile ion like phosphate, it can have a big, the presence of root hairs can have a big effect. Mycorrhizae are an analogous, something analogous to root hairs because they also increase the volume of soil that's explored by this root fungus symbiosis. And they've also been shown to aid dramatically in phosphorus uptake, particularly, also in sometimes in water. And mycorrhizal fungi are found all over the place too. It's rare to find a situation where mycorrhizal fungi are not present. They function kind of like root hairs. So the root is, you know, it sounds like a simple structure. You have the root and you have the soil, but that interface between the root and the soil is not so distinct, especially with the presence of root hairs and with mycorrhizal fungus. Also, there's a whole microbial community that forms around the living root. Why is that? In large part, it's because roots exude carbon and other substances into the soil around themselves. And it's an odd thing when you think about it. Why does the plant that spends so much energy and effort fixing carbon into sucrose, let's say, why does the plant transport that sucrose to the root and out into the soil? Makes no sense, right? Because it doesn't hurt. Sometimes it actually helps. Here's a paper where these people in Utah looked at Indian rice grass. So this is a grass that grows in fairly xeric environment in this part of the continent. And they wanted to answer the question, water uptake by rhizome sheets of this grass, a numerical simulation. They wanted to answer the question, okay, there are two ways that the presence of this rhizosheath, this area around the root that's been influenced by exudates from the root and has altered hydraulic properties from the rest of the soil. There are two ways they could think of that may aid water uptake by the plant. In the first case, that altered soil around the root may contain more water. It just may hold more water than the bulk soil can, and so more water there, easier to uptake by the plant. In the second case, they looked at, or they considered the situation of these exudates in the rhizosheath, the rhizosphere around the root, change the hydraulic properties of the soil and thus make water movement in the soil easier, right? They increase the hydraulic conductivity of the soil. So they did a numerical study, and what they found out was it's a far bigger effect is by altering the hydraulic conductivity of the soil than by actually storing water in that sheath around the root. So this grass, by exuding these substances around the roots, changes the hydraulic conductance, hydraulic conductivity of the soil around the root, and makes it easier for the water to move from the bulk soil into the root, increasing hydraulic conductance. So there may be benefits that are subtle for the reason roots lose carbon like this and sustain a microbial community around themselves that's different from that in the bulk of the soil. I don't think this stuff grows near Lincoln. I think it's found mainly in the western parts. Okay. Well, let me talk a little bit about water uptake by roots. A couple of experiments showing the rate of water uptake per length of root and the distance back from the tip of the root. Now, the first picture I showed was the most distal 1 millimeter of the root, where the cell division and the differentiation is taking place. Here now, this axis is 2, 4, 8 centimeters back from the tip of the root. So all that cell stuff is happening right here. And this is going way back from the tip of the root. But if you look at the rate of water uptake per root length, the highest rates are closer to the closest to the tip of the root. And lower rates are found further back in the root. This shows two plants, barley and pumpkin, and shows similar behavior. That the highest rates near the tip, but lower rates further back, but not zero rates. These older parts of the roots, even though they get highly suberized, still are taking up significant amount of water. Particularly because if you look at a root system, there's a lot more root length in this region than there is in this region for a typical root system. There's a lot more older roots around than really young roots. Here's another experiment that shows the same thing. Rate of water uptake per centimeter of root, and here's for 12 centimeters. So again, the highest rates near the tip, lower but non-zero rates further back from the tip. And in this set of experiments, they looked at two relative humidities, high and low. Less atmospheric demand, more atmospheric demand. In other words, higher transpiration rate here than here. And when they put the plants in a drier atmosphere and increased the transpiration rate, that increase in water uptake came from the older parts of the root, not from the young. Kind of interesting. So, although these rates are much lower than rates found near the tip, they're still really important for water root system. And after all, the water balance of the plant, it's one of those calculus problems. You got a rate of uptake by the root system, a different rate of water lost by the above ground parts of the plant, and the plant's job is to balance those two and make sure that it doesn't run out of water. It's like the classic calculus problem of a tank that's being filled and drained at the same time. So, but the plant's got to do calculus. It's got to make sure that this thing happens. Can't do much about water uptake here. Can do a little bit, but what it can do is really control the rate of water loss above ground through variations in stomata conductance, which is where we'll get to after roots, xylem, phloem, then we get to stomata. All right, so keep that up. Okay, so just like pressure volume curve for a plant, here's a relationship for a soil between soil water content and soil water potential. And one reason, well, a couple of reasons for showing this. One is because it's got really weird units on it for water potential. And the other ones, it shows different soils, how their water relations differ. So here's soil water content, and this is volumetric water content now, cubic meters of water per cubic meter of soil. Volumetric water content, and the water potential now, PF number. What's PF number? It's a weird way of expressing potentials. The base 10 log of the soil water pressure head in centimeters. There you go. It's kind of funny that there's so many different ways of dealing with water, especially water potential. You gotta get used to it. Anyway, a PF of 2, this value right here, is field capacity, about minus 0.02 megapascals, total water potential. PF value of 4.2 is permanent wilting point, minus 1.5 megapascals. So, total water potential is 0 and getting drier and drier. You see that this relationship between water content and water potential depends on what kind of soil you have. So fine sand, silt, clay, peat, coarse sand, it varies a lot. Also, not shown very easily here. Well, okay, so this is base 10 logs, right? These are order of magnitude differences in water potential. That shows a little clearer on this graph. where here is the volumetric water content, and here's the water potential of the soil. And this water potential now is in millimeters of water, I guess. But you can see that this is a log scale, 10 to the 6th, 5th, 4th, 3rd. These are order of magnitude differences in the water potential of the soil with relatively small changes in water content of the soil. So as the soil loses water, its water potential gets more and more and more negative. And that's a dramatic change in water potential. That's one aspect of soil-water relations that we have to consider. The other one that's just as important is that the hydraulic conductivity also is a strong function of the soil water content. So here's a graph of hydraulic conductivity, this Taylor, and the volumetric water content of the soil. These are just 3 different soil types with funny names. Here you see that as the soil water content goes from 0.3 to 0.2, let's say for any of these, you have orders of magnitude decrease in the hydraulic conductivity of the soil. And so, remember, we have this, the rate at which the plant can absorb water from the soil depends on the difference in the water potential between the root system, the cells in the root system, and the water potential of the soil. And it also depends on the hydraulic conductivity of the soil. So, let's say the uptake rate from the soil depends on the difference between, we could talk about a cell in the root. So the total water potential in the root minus the total water potential in the soil. That's the driving force for the water movement. But then you also have a soil hydraulic conductivity term. Well, you use K, but on that. Use this letter K. Okay. So, in a drying soil, if the root water potential stays constant, as the soil dries, this total water potential becomes more and more and more negative. So this difference decreases. And at the same time, the soil hydraulic conductivity gets smaller and smaller and smaller. So you've got this term of the equation decreasing, you've got this term decreasing, and so the uptake really goes down fast as the soil dries out. Okay, so that's a dilemma, because the plant has to deal with it, right? And the other dilemma is you've got the dry atmosphere around the plant. So we went through this a few weeks ago. We don't have to do it again. The water potential of the air is given by this equation, which is related to the relative humidity of the air. And here are some things. And what we could do, here's the average relative humidity for us at local noon in July, 45%. Believe it or not, it's increasing. Anyway, if you put 45% in here with some reasonable temperatures, you can figure out the water potential of the air, of the water vapor in the air. So for example, let's assume it's 25 C, 60% relative humidity. The water potential of the air is minus 70 megapascals. in a drier situation, 35 degrees C with 15% relative humidity, not out of the question. What's this red blob here? Less than 20% RH. Nevada, yeah. Well, you can guess that, right? That's not an unreasonable, not unreasonable conditions. The water potential of the air is minus 269 megapascals. It's really dry. So the root system then has to supply an amount of water roughly the same as what's going out the top of the plant. Otherwise, all the cells in the plant are going to lose water. And their water potential gets more negative, and it's more difficult for the plant to function. Well, thinking like in that environment. Right? It's this combination of, okay, so it's thinking of water stress. Water stress can definitely be imposed by a drying soil, with the water potential becoming more and more negative, the hydraulic conductivity being reduced, and the plant can't take up enough water. But it can also be caused by a dry atmosphere. And this water stress is this combination of both ends of the system acting on the plant. Right? So here's our chart of water potentials in a drying soil and in a plant that's existing in that drying soil. I showed this before. What do I say? Oh yeah. So if the water potential of the plant stays constant, as the soil dries out, less and less water is going to be taken up by the plant because of this decrease in the soil water. And at the same time, decrease in hydraulic conductivity. So water stress is not just the effects of drying soil, but it's also the effects of a very dry atmosphere. That's the plant has little control over. The transpiration rate, remember, for a plant, we can write as, now I'll write total leaf conductance for water vapor. And the driving force is the saturation vapor pressure at the leaf temperature minus the vapor pressure of the air divided by the total pressure. So it's the mole fraction of water vapor inside the airspace of the leaf minus the mole fraction of water vapor in the atmosphere around the plant. That's the driving force for transpiration, for water moving from inside the leaf to the atmosphere. And here's the leaf conductance. So as the air dries out, this value is smaller. As the temperature increases, this value gets a lot bigger. So the transpirational demand really increases as temperatures go up and humidities go down. And if the root system can't supply that, can't satisfy that demand, something's got to give. And in plants, one of the first things that happen we already know, right? Talked about it for a couple of weeks. Cells stop expanding in the leaf. All right, that's a long-term solution. Short-term solution plant have is to reduce the total leaf conductance for water vapor. This is made up of boundary layer conductance and stomatal conductance. And the plant has, most plants, many plants tightly control their stomatal conductance to make sure that these things don't get out of balance and the plant doesn't use too much water. But just a long-winded way of saying that water stress isn't just determined by the soil water conditions. But the atmosphere has a big role to play.
Although, what do you know anything about the relationship between dry soil and dry atmosphere? Those kind of go.
Yeah. They go together. Yeah. Right. And what's more, well, a couple of things. Yeah, usually the dry atmosphere and the dry soil can go together. Also, when considering the control of stomatal conductance, the leaf water potential doesn't have a lot to do with stomatal conductance. You might think, oh, well, as the leaf water potential gets more negative, the stomatal will close. But that happens, but it's just a correlation. And it's the water relations of the soil and of the root system in the soil have a big influence on the stomatal conductance. So as the soil dries out, the roots signal to the stomata up above ground, close. And they'll close. Also, dry air has a direct influence on closing stomata. But you're right, usually dry soil, dry air can go together. Yeah, that's a good thing to keep in mind. All right. So that's roots. Brief introduction. Any questions about roots? What's going on below ground? Root systems are notoriously difficult to deal with, especially in field studies, right? Nobody, has anybody measured root biomass? Yeah? Not easy. Above ground biomass is hard enough, but root biomass, yes. So people don't usually make those measurements of root systems. It takes too much work, and it's tedious work, and it's not very well paying work. Right? So people don't tend to do a lot of it, but it's really important and it's really interesting. Sometimes. Anyway, we've had a project going on at the Eastern Nebraska Research and Extension Center near me, right, since 2001. So we're in our 18th year of project. And it's looking at carbon budgets, carbon pool, carbon fluxes, like that. And ultimately soil carbon sequestration. And it's with maize and soybean